And we are. All right, so electrical power. This next formula looks a lot like Ohm's law, but it's going to be called the power formula. Okay, so let's work it out. So power is just defined at the rate at which work is done. Okay, you know your cars, right? For example, you know, if you want to buy a high performance car, what's one of the main numbers you're going to look at? One more time. Nothing. Horse mileage, right? But let's say the car's brand new, right? You're going to look at horsepower, right? Well, what's horsepower, right? And it's usually like a couple hundred horsepower, right? You buy one of those Dodge Challenger Hellcats and you're getting like 800 horsepower, right? Ridiculous. But the point is that power and horsepower in cars is just saying the rate at which the work is done, right? If something can do more quickly, it has more power, right? One horse can pull a wagon up a hill. Two horses can pull that wagon up the hill faster. Same wagon, two horses do it faster than one horse. Okay, so power is the rate at which work is done. Work is a general idea that we move things, right? So work is moving things, changing the position, velocity of things, right? Spinning your electric motor, turning on your flashlight, right? That's requires work to be done, okay? So I don't mean clock in, clock out of your job. When we mean work, we mean doing something, affecting the state of some material, okay? Yeah, so they give an example here, you know, two cars reach the top of the hill, right? Requires the same amount of work, right? You take a Volkswagen Beetle and drive it to the top of a hill, right? It's going to get to the top of the hill, right? But you take your, you know, your whatever, the Dodge Hellcat Charger thing, right? That fast, super fast, high-powered car. It's going to get to the top of the hill faster, right? Why? Because it has more power, right? It's supercharged, right? It can put the power. It can use the power in a at a faster rate. It can do the work at a higher, quicker rate. Okay. Said simply, the high-powered car gets to the top of the hill quicker.
So, if we have higher kVp,
There you go.
we can take more. We can get more X-rays.
Your X-ray beam will have more power.
Your X-ray can be more. Okay.
Be more energetic. You're thinking the right things.
I'm in the
Oh, I think you have a hand up. Okay, then go Taylor.
Doesn't that have to do with something about the generator, like how powerful the generator is?
Yeah, how efficient the generator is. Yeah, absolutely. Yeah. So power. You know, when you buy, and I'm going to give it away here. You know, when I talked earlier about wattage, right? Your microwave, right? If you have a 1,000-watt microwave and you put next to it a 1,500-watt microwave, well, the 1,500-watt microwave is going to cook your food faster, right? That's doing the work of cooking your food, but faster. That's the rate. The rate has increased, right? More power equals a faster rate of doing something, right? We gave the example of cars going up a hill or a horse pulling a wagon up a hill, right? But it's the same in electricity and electric devices, right? More power equals we do more work more quickly, okay? Work is just, you know, changing the position of something, let's say. Okay, so work done is equivalent to energy spent. Okay, power is the rate at which energy is used. So power equals energy divided by time. This is not the formulation of the power formula that I'm gonna invoke, but this is just an example of what we're talking about. So I'm about to invoke the power formula, so we'll get there. Anyways, moving on. Total power of any system, any system can be thought of as a combination of the quantity of work done multiplied by the quality of work, right? How quickly you do that work, right? If you're high quality, then you can get the work done faster. Same quantity of work can be done faster with more power. Intensity times force is the same thing. All right, let me just go ahead and move to it because I think it's easier when we actually just get to the actual thing. So the unit for electrical power is the watt. Okay. A kilowatt would be 1,000 watts. Kilo for 1,000, and we deal with thousands of watts of power in our X-ray equipment, but let's start with just the base unit, the watt. Okay, the watt is the rate at which electricity is used. That's why your electric bill is listed in kilowatt hours, right? How much power you're using. This is rate, that is rate multiplied by time to get the total electricity used. If I tell you, your house is operating at 1 kilowatt, well, 1 kilowatt over what amount of time, right? 1 kilowatt for the whole day? Or 1 kilowatt for an hour, right? So a kilowatt hour, right? Like one kilowatt hour is using 1 kilowatts of power over 1 hour's time. So in 10 hours, you would use 10 kilowatts. Okay, so look at your electric bill next time you get it. Look at how many kilowatt hours you used. And you can divide that by the number of days that it has been the recording period, right? You can figure out how much power you're using per day. And what's nice about the electric bills is usually they kind of give you a graph, like a bar graph of when your busy high power days are, right? Or even break it down to you can even break it down to the times of day on those graphs usually, so you can kind of tell when you're using more power or less. Parenthetically, they charge you more power at certain times of day. I don't know that you know that, but there are times of day when everyone's home using power is the time when power is the most expensive, right? So power costs money because it costs energy, right? Someone somewhere had to produce that energy for you to use, so you got to pay for it. Yeah.
I was pretty mind blown when I switched the difference between the two bulbs. So I was looking for just like a general, like the little bulb, right?
Mhm.
Not those big long ones. I was
Sure,
looking for a
just regular
general
bulb.
bulb to switch out, and for one of the ones I had in my house. The 60 watt produced a lot more heat. Obviously, you don't want to touch the light bulb when it's on because it's really hot. But I was surprised when I saw that it was 60 watts, and I went to Walmart to go buy some that were
LED.
anywhere between 5 to 10 watts, 12 watts, because I'm trying to conserve energy for my reasons. So when I switched it out, the brightness is almost the same. The hotter one, the 60 watts, still going to be a little bit more brighter, but it does produce heat as well.
So what's that heat?
The heat.
That heat is waste energy, right?
It's wasted energy.
Your other one that runs at a lower wattage doesn't produce the heat because it's using the energy more efficiently, right? So that all that extra wattage from that 60 watt bulb is not producing extra light, it's producing waste energy because it's a less efficient bulb, right? So you guys know, like, most houses now have almost entirely switched over to using LED lights, right? Light emitting diode lights, right? If you ever bought LED lights, it'll tell you the wattage, it's like 6 watts or whatever, right? And it'll say like equivalent to a 60 watt light bulb, right? That means if you had a fluorescent or incandescent light bulb, which pulled 60 watts of power, and then you plugged in this LED light bulb that only uses 6 watts of power, it's going to produce the same amount of light, right? But as Javier was saying, it's not going to heat up like the 60 watt light bulb was, because the 60 watt light bulb, while it produces light, produces a lot of waste heat too. So the LED light uses 10 times less, in this analogy I'm giving you, 10 times less energy, 10 times less power, consumes power at a rate 10 times slower than the 60 watt light bulb does, but it still puts out the same amount of light that the 60 watt bulb did. Yeah.
LED lights, do you know like what's the value of like 6K? Like, you know how like LED
Yeah, that's telling you the
6K?
that's telling you the in Kelvin, it's telling you the wavelength, it's telling you the wavelength of light. So the different numbers are telling you what color the light's going to be. Wavelength of light changes color. Higher energy means shorter wavelength, means bluer color, right? So if you want if you want a more relaxing light bulb, you want something that's got the yellows and the reds and stuff in it. So it's going to be a lower temperature light bulb. So when they say temperature, they don't actually mean like temperature that you can. They mean the wavelength of the light coming off. Yeah. So so like if you got those 6,000 and 8,000 Kelvin lights, right? They're producing more. They're using more energy, but they're producing wavelengths of light that are going to be way bluer, right? Yep. If you ever bought lights for your car, it's the same way, right? You can buy different colored headlights for your car, right? To some extent, you can change the color, right? And that's all given by the wavelength of the light produced. Anyways, and the power used. Okay, good. So I think we're on the right track here. The moral of the story is go buy LED bulbs for your house if you don't have them already. It uses like 10 times less power. Okay. All right. And they last for so much longer. I'm not a.
Mine were like guaranteed for like 6 years
Yeah.
or something like that.
Yeah, they don't always last that as long as they say, but they last longer than regular bulbs do. All right, moving on. Okay, so the power, the unit for power is the watt, but how do we figure out what power is? How much power? Remember the three things that were characteristics of the electric circuits. There was something pushing the electrons, the potential difference voltage. There was the electrons moving, the current, and something resisting that current. Okay? Turns out all you need to know to figure out how much power is being used is you need to know the voltage, the push, and the amperage, the current. Okay? Those two things multiplied together tell you how much power you have. Okay? So what's the voltage for the household plugs that I've been talking about?
115.
110, 115, 120. For now, let's call it 110. It varies. If you put if you take a multimeter and test it, you might get 110, you might get 115, 112, 120, but anywhere in that ballpark, it's fine. But for the purpose of this, let's pick a number. Let's say 110. Okay. So your voltage, let's say, is 110, and let's say you know that your toaster draws 10 amps. Okay. 110 volts and 10 amps. 110 times 10 is 1100. So the power of that toaster, let's say, would be 1100 what? Watts, right? Because watts is the unit for power. You know the voltage. So what's nice is, like for any household device, right? I don't need to tell you the voltage because you know the voltage. Because that's what your wall puts out. You know what your wall puts out. It's a given number, okay? We could treat it like a constant, really, okay? Because you know what it puts out. So then all you need to tell me is you need to either tell me what the wattage is for the device and let me figure out the amperage, or you tell me the amperage and I can tell you the wattage, okay? I encourage you to, when you go home, start looking at your refrigerator. Pull your refrigerator out away from the wall. Open up the manual or whatever, but look at what the wattage is for your refrigerator, right? Look at what your computer chargers list wattage, amperage, and voltage on them. Okay, your phone's little charger bricks should say that as well. I mean, they may not nowadays, but anyways, the point is all electric devices have these three things in common, and you can figure out one of them if you know the other two, or you can figure out, in this case, power if you know amperage and voltage. Same. Oh, yeah, go ahead.
When I was doing this, I was having a hard time remembering what goes where.
Okay.
Is there the challenge is reading the question. I think you said it.
Yeah.
Throw away the useless information, and I get that, but it's like when I've got the two things or the two different units, how do I, if I'm on